So this is our second video relating to rates of reaction, and in this video we're going to look at catalysts. So a catalyst is a chemical that you can add to a reaction which makes it speed up, and catalysts really speed up the rate of reaction. However, what makes a catalyst special is that they remain unchanged at the end of the reaction. Now, if you do biology, the equivalent of a catalyst in biology is an enzyme. You know that an enzyme helps make a chemical reaction happen, but that enzyme can be used over and over and over again. Well, that's what a catalyst is. And catalysts are really important in industry because they allow reactions to run at lower temperatures, and they also allow reactions to go faster, which helps save a lot of money in industrial processes. Now, how catalysts work is different to any of the four factors that we looked at in the previous video. Catalysts work by actually giving the reactants a new way of reacting with one another that requires less activation energy. And remember, from National 5, activation energy is that energy needed for reaction to start. Now, at higher, we now need to understand what really is meant by activation energy. It's the energy needed for your reactants to form something called an activated complex. And this activated complex is a sort of intermediate that forms in the middle of the reaction. And once it forms, the intermediate complex, or the activated complex, is what will transform into the product. So you give the reactants energy, they form an activated complex, and it's the activated complex that then turns into the products. And the activation energy is the energy needed to form that activated complex. Now we can sort of represent a reaction using a diagram like this. This is known as a potential energy diagram. And we'll look at this in more detail in a Unit 3 topic related to energy and reactions. But we can see the letter R represents reactants, the letter P represents products, and the blue line is sort of the reaction as it happens. Now that blue line always goes up first, and it forms a hill. The top of that hill is your activated complex. And the difference between the activated complex and your reactants is known as the activation energy, which is sometimes given the abbreviation a capital E and then a small a. E for energy, A for activation. And so the reactants, they sort of need this energy to form the activated complex. Now catalysts, what they do is they lower the energy of the activated complex. They make a new activated complex that involves the catalyst, and it needs less energy. So the reaction happens in a completely different way when you add a catalyst. But always what's happening overall, and all you need to know, is that a catalyst lowers the activation energy by lowering the energy of the activated complex. We can represent this change and understand how catalysts work on another type of diagram known as a kinetic energy diagram, or an energy distribution diagram. Now in this doesn't look at reactants and products, it just looks at all the particles in your reaction. So you have energy along the bottom, this time it's kinetic energy, moving energy, and then we've got a number of molecules. And so that curve, that bell-shaped curve, represents all the particles in your reaction. And then we have this dotted vertical line, which represents our activation energy. And all the particles that are to the right of the activation energy are the particles that have enough energy to turn a collision into a reaction. So we want that shaded in area of the graph to be as big as possible, because that will mean that we've got lots of reactant particles that can react because they've got enough energy. Now, when we add a catalyst, what this does is, because it lowers the activation energy, it moves that dashed line to the left. And by moving it to the left, by making it lower, you can see that the shaded in area on the right-hand side is now a lot bigger, which means we have a lot more particles that have the required activation energy, and that reaction will then be much, much faster. We can also use these energy diagrams to show you why temperature has such a good effect on the rate of reaction. So that's what we'll move on to next. So again, activation energy, when you add a catalyst, it moves to the left, so more particles end up with enough energy to react. Now, we take our diagram. This is not involving a catalyst, but this time what we do is we increase the temperature. Now, when we change the temperature, we're changing the energy of the particles. And what ends up happening to that curve, if we increase temperature, is that it gets wider and flatter. So as we increase the temperature, the graph gets less tall, but it gets a lot wider, which means if we look at the shaded in area, there's now a lot more particles that have enough energy to react. The activation energy hasn't changed, it's just the number of particles with enough energy has changed. So when temperature increases, activation energy doesn't change, but more particles have enough energy. The graph gets flatter and wider, or you can remember it flatter and fatter if that helps, and this speeds up the rate of reaction. When we do the opposite, so if we decrease temperature, if the graph gets flatter and fatter whenever we increase temperature, it gets taller and thinner whenever we decrease temperature. So the line you can see now has hardly any particles with energy greater than the activation energy. So the EA doesn't change, but less particles have enough energy. It's because the curve gets taller and narrower, and this results in the reactions slowing down. So from this video, what you need to be able to remember is what a catalyst is, a chemical that speeds up the rate of reaction by lowering activation energy, but is unchanged. You need to remember that the potential energy graph, you just make the hump lower by lowering the activation energy. And on the kinetic energy molecules, catalysts move the activation energy to the left. Increasing temperature makes the curve flatter and fatter. Decreasing temperature makes the curve taller and thinner. And this results in more particles having the activation energy when you increase temperature, and less particles having the activation energy when you decrease the temperature.